Hello, everyone. My name is Anubrata Das. I am a fourth-year PhD student at the School of Information at University of Texas at Austin. Today, I had the pleasure of presenting a work done by one of the former students at our university, Pratik Chaudhary, and my advisor, Dr. Matthew Lees. The title of the paper I'll be presenting is "You Are What You Tweet: Profiling Users by Past Tweets to Predict Hate Speech." Hate speech detection online is a large scale and continually growing problem. To get a sense of how large scale the problem is, we can see that this report on the first quarter of 2020, Facebook alone removed 9.6 million hate speech from the platform. This number, according to the Facebook website, in Q4 2021 is around 17.6 million. To address this problem at scale, other than human efforts, we also need at least some degree of automated hate speech detection. And automated hate speech detection typically is framed as a content-based classification task. It does not capture often additional context where the hate speech might appear. Another key issue that has been pointed out in the literature is hate speech has the case of repeated offenders, which means the user who is known to write hate speech messages may do so again. We see similar empirical evidence from the Facebook integrated research as well, where in the report they point out the user or group that has posted validating content in the past may be prone to doing so more often in the future. So we can see that prolific haters are a problem, and this translates when we look into automated hate speech detection data sets, where it tries to capture the real world phenomena in the context of a data set. So in this graph, we have three data sets. I'll talk about the details of the data set later. But for now, let's look at this x-axis, which is the number of users who posted hateful tweets. And on the y-axis is the number of hateful tweets. So you can see that here, it's kind of a concentrated part of all these three data sets where a handful of users actually generate far more hate speech than others. So in this study, to tap into this phenomenon, we along with tweet content, we captured user history by including previous tweets by the same user. And this is useful because modeling user priors is informative and complementary to detecting hate speech based on the content alone. Some related work has attempted capturing context in the past, and they do it slightly differently from our approach. In one work, Dadwer et al., they profile users by the past number of obscene words used in tweets. Wasem and Harvey infer user gender and location as additional features. Other than this kind of textual features, also several work has looked into the graphical nature of Twitter, where they analyze retweet graphs to detect how hate speech spreads and also profile hateful users via follower graphs. In this work, we established a baseline model, which is an extension of two prior work, Barjatya et al. In 2017 and Arango et al. In 2019. So the baseline model is a two-stage model. The first stage is for extracting task-specific embeddings, and the second stage is for the final content-only classification. So what happens in the first stage is we initialize an LSTM-based classifier or LSTM layer based on GloVe embeddings, which is a pre-trained set of static embeddings. And then a cross-entropy loss is used for this classification task. Let's imagine for this case, hate versus non-hate, and kind of propagate back and fine-tune the embeddings in the LSTM layer. Then this extracted task-specific embeddings are used for the final layers of classification, where we have token level embedding for this task, and then once a tweet level embedding is obtained by averaging over all the token level embeddings. And finally, a gradient boosted tree is used for the classification. Now, the baseline model is augmented with user timeline, where in terms of capturing user history, this model captures last 20 tweets by each user. And the Twitter API kind of allows us only capture 20 tweets at one go. There are other ways to collect larger data and capture larger context, but for the simplicity of the work here, we have only stuck to 20 tweets. And one of the other advantages that you could really do this pretty quickly and collect this 20 tweet snapshot in a real-time system. So we kind of utilize the task-specific token level embeddings from the previous layer and pass on this last 20 tweets per user and obtain user level embedding. So what actually happens there is for each tweet, each token level embeddings is averaged, and then for all of the tweets, they're averaged across to obtain one user history embedding. Now, this one user history embedding is concatenated to the Twitter level embedding and gets passed on to a gradient boosted tree for hate versus non-hate final classification. For this work, the data sets are Wassim and Hovey, introduced in 2016, and Davidson, introduced in 2017. For Wassim and Hovey dataset, the labels are racism, sexism, and neither. And note that this is an expert labeled dataset. One key issue to note here on Twitter-specific research is the Twitter policy stops researchers from sharing the exact tweet content, and they're encouraged to share only the tweet IDs for the community to use. Now, when you get the tweet IDs downloaded and try to crawl back the original data set, what happens, especially in the case of hate speech, some of these tweets have already been probably removed either by the user themselves or by the platform moderation team or what have you. So when we crawled back the Wassim and Hovey dataset, we only could obtain 10K tweets and only 6 racist tweets over 1,400 plus users. For Davidson, we have 3 labels: hate, offensive, and neither. In contrast to Wassim and Hovey, Davidson dataset is crowd labeled, and it has 18K tweets over 741 users. In a later work, Arango et al. Identified 2 key issues with Wassim and Hovey and Davidson dataset. Number one, as a few prolific haters dominate the dataset, as we saw recalling the graph that there's kind of a concentrated set of tweets that come from only a very few users. And the second part is that tweets by the same user might appear in both train and test. Just clarifying, it's not the same tweet appearing in train and test, but tweets from the same user appearing in train and test. What happens in that case is if you have prolific haters and if the model just picks up on the artifacts or the style of a particular user, then that kind of leaks and may just help the model perform better just because it has seen similar tweets from the same user. To address this issue, Arango just draws on Davidson and Wassim and Hovey and kind of clubs the data sets together, merges the data set together. And they also suggest that the train and test split by the users, so that a user whose tweets are appearing in the training data should not appear in the test set and vice versa. And in this case, we got 5.4K tweets over 746 users. One thing to note here that the user per tweet, user to tweet ratio is much better in the context of Arango dataset. So in our experimental setup, we have Wassim and Hovey, and on that data set, we perform binary classification. As you recall, there was only 6 racist tweets that we could obtain, so we kind of break it down to a sexism versus non-binary classification instead of a 3-label original that the original data set have introduced. For Davidson dataset, it's a ternary classification across hate, offensive, and neither. Arango is a merge of 2 labels where it's just hate versus non-hate, and hate includes sexism, hate, and offensive tweets. Although Arango pointed out that the right way to perform train test split is by the users to avoid leakage, for sake of completion and comparison with the existing work, we report both split by tweets and split by users in the context of this work. Here is a distilled version of the original result. In the paper, we have an extensive set of experiments reporting and comparing different setups for the experiment across datasets, as well as different classifiers and different measures. In this case, we're just looking at the micro F1 score across the baseline and the timeline across 3 datasets. You can see that Wasim and Harvey has 76.0 F1 score for baseline, and with timeline it goes up to 79.3. So we kind of see a good amount of improvement by using Twitter history. But when we go to Davidson, we do not see such improvement, and we see that 88.9 to 88.8. The number is very less. The difference is very less, at least in this result, but this kind of varies a lot if you look at the larger table in our paper. And in case of Arango, we see that this difference is also small. It's 79.8 to 80.1. So we see a moderate improvement, but we see kind of consistent improvement across different setups. Now, what may have caused this form of discrepancy across these data sets, that the model performs well on one data set, doesn't perform as well on the other? So just recalling back our graph, where on the y-axis we have users, on the x-axis we have tweets per hateful tweets per user, and here you can see that that a handful of prolific haters kind of end up taking a lot of space in the data set, which means 44%, like concretely 44% of the sexist tweets in Wasim and Harvey comes from one single user. So this raises an interesting question about how to construct a good benchmark for hate speech. So if data sets consist tweets from only a handful of people, any algorithm built on them will probably end up modeling just those users' behaviors. Now, would such a method generalize its practice? And it kind of creates a point of contention that to what extent this kind of data set actually capturing the real world phenomenon, and do we see that in real world there are a handful of users and that's actually a useful thing to do, or we need to take a much more general approach towards creating this benchmark so that we can capture hate speech, let's say by new users, which the model hasn't seen before. The key takeaways, once again, from the results is splitting users lead to cleaner experimental setup. This is consistent with the prior work from Arango. And we also conclude that it's really hard to compare results across datasets due to many variations across them. So number one is there is no agreement on a consistent task formulation. We saw that across 3 datasets, the labels are completely different. So annotation categories and process itself, like whether it's expert labeled or it's crowd labeled, how the data have been collected in real life, that also kind of introduces variation in performance. And then there is this case of possible missing tweets due to platform sharing restrictions. There is some ethical considerations in the context of this work, that user profiling is helpful for better detecting hate speech. However, there is a potential challenge. What happens in case of there is a reformed hater who wants to engage with the platform again? And due to capturing the history, the model might always flag anything posted by them, although they may have reformed and doesn't actually show hateful behavior anymore. So a couple of possible remedies are decay the weights assigned to past tweets by age so that the effect wears off as the user shows signs of not engaging in hateful activities anymore, or restrict the history to a recent window in case of 20 tweets, or you could imagine kind of playing around with that window. In practice, though, the opposite problem is much more prominent, where bad actors who get suspended from platforms often circumvent this kind of suspension by creating a new account and continue spreading hate speech. We identify a set of future works, a better data set, better contextual modeling. We could engage human in the loop solutions through explainable algorithms to enhance or help moderator accuracy and speed. And there is also a question of balancing fairness with accuracy and ethics of user profiling, whether there is a tendency towards certain gender or towards certain ethnicity, etc. And we need to be aware of this kind of fairness issues that might show up in hate speech detection methods. One quick plug here about another work that's from our lab, introduce a data set. This is from NeurIPS 2021, where introduce a method of creating a hate speech detection dataset along with sharing a dataset for the community. Typically, what happens in hate speech detection work is it starts with a set of keywords, and these keywords are, imagine a set of obscene keywords, or set of hateful keywords, or a set of vulgar tokens, etc. What happens is you start from that list and then search, let's say, Twitter, to get all the tweets that kind of contain those kind of hateful comments. But there exists a case where there are hate speech that does not contain this kind of word. For example, when you hold all 3 branches and still can't get anything done, you must be a Republican. This is a hateful tweet to a particular political belief. And this does not get captured in data sets that are reliant on tokens. So this particular work uses information retrieval techniques to maximize annotation efficiency while improving relative coverage and capture hate speech that are relatively diverse from existing data sets. Thank you so much for listening. I thank the Good Systems, so Wipro, Knight Foundation, Micron Foundation, and Texas Advanced Computing Center for helping and sponsoring some of this work. Once again, this is not my work. I'm presenting somebody else's work, and happy to take any questions and take it back with the authors. Thank you so much.